So the noise which we use in analog communication is called as white noise, or it is also called as wideband noise. So the noise is called as white noise or wideband noise. So why it is called as white noise is its power spectral density is this. The power spectral density of the white noise is this. As white color affects all the colors equally, similarly this white noise will affect all the frequencies equally. So that is why this noise is called as white noise with power spectral density N0 by 2. So with the power spectral density N0 by 2. So if white noise is passed through a band pass filter, then the output of this band pass filter, or the noise at the output of this band pass filter, is called as narrow band noise. So white noise is also called as wideband noise. Wideband noise because it affects all the frequencies equally. So since it affects all the frequencies, it is called as wideband noise. So when it is passed through band pass filter, now it is affecting only certain range of frequencies. So that is the reason why the output noise at the output of band pass filter is called as narrow band noise. So figure of merit. So at the receiver end, so the input will be the signal, that is the modulated signal, plus the noise which is added in the communication channel. So at the output also there will be some noise because receiver cannot eliminate the complete noise. So thus the output signal is represented by S0 and noise is represented by N0. So the signal to noise ratio at the input of receiver is given by Si by Ni. Similarly, the signal to noise ratio at the output of the receiver is given by S0 by N0. So figure of merit is defined as the ratio of signal to noise ratio at the output of receiver to signal to noise ratio at the input of receiver. So for a good receiver, the figure of merit must be as maximum as possible. So it should be always very much greater than 1. So noise figure of a communication system, communication receiver, is the inverse of figure of merit. So figure of merit is defined as the ratio of signal to noise ratio at the output of receiver to signal to noise ratio at the input of receiver. So the inverse of it is signal to noise ratio at the input of receiver divided by signal to noise ratio at the output of receiver. As we have seen, figure of merit must be as maximum as possible for a good communication receiver to be operated under the presence of noise. Similarly, the noise figure must be less for a good communication receiver to be able to operate under the noise. So when DSBSC signal is passed through channel, so there will be addition of white noise. So S of T of DSBSC, that is DSBSC modulated signal plus white noise, is added in the channel. So the noise which is added in the channel is assumed as white noise. When it is passed through band pass filter, you will get a narrow band noise here. So narrow band noise is obtained, and this is still S of T of DSBSC. And when it is passed through the receiver, so the signal power is the power of the S of T is the signal power SI. The power of narrow band noise is NI, and when it is passed through the product modulator, so when it is passed through the product modulator, whose other input is AC cos of 2 pi FCT, that is the, and next it is passed through a low pass filter. So at the output you will get the message signal plus noise signal. So this is S0, and then the power present in the noise is N0. So we'll calculate S0 by N0 here, and we'll calculate SI by NI here in the case of DSBSC. So the modulator which we use for demodulating the DSBSC signal is called, so this part is called as synchronous detector. So the detector which we use is called as synchronous detector. Okay, so if we calculate the figure of merit for DSBSC signal, we'll get it as 1. So the figure of merit of DSBSC is equal to 1. So in the case of SSB also, when SSB signal is passed through the channel, white noise will get added, and same synchronous detector is used as the demodulator for SSB also, and S0 by N0 is calculated the output of receiver, which is called as signal to noise ratio at the output of receiver, and SI by NI is calculated the input of receiver, which is called as signal to noise ratio at the input of receiver, and the ratio of these two, signal to noise ratio to signal to noise ratio at the output of receiver to signal to noise ratio at the input of receiver, is called as figure of merit. So if you do the analysis and calculate the figure of merit for SSB also, the figure of merit will remain same, which is equal to DSBSC, and it is equal to unity. In case of AM, so when AM modulated signal is transmitted using either square law modulator or switching modulator, so then white noise gets added in the channel, and this is S of T of AM. So the detector which is used for detection of AM signals is envelope detector. So it is passed through envelope detector, and the detector output will consist of the message signal plus noise signal. So we'll calculate the noise at the output, signal power at the output and noise power at the output, and similarly here you will have S of T of AM plus narrow band noise. So we'll calculate SI and NI at the input of this envelope detector. So the figure of merit, after analysis, the figure of merit in the case of AM is obtained as Ka square P divided by 1 plus Ka square P, where Ka is called as amplitude sensitivity of modulator. Amplitude sensitivity of the modulator, and P is the power of the message signal m of t. So the power of m of t. For single tone case, so P is equal to am square by 2, because we will consider m of t as am cos 2 pi fm into t in single tone case. So power is now am square by 2. Then figure of merit is equal to ka square am square by 2 by 1 plus ka square am square by 2. So ka into am, we know that modulation index in am is given by ka into am, where mu represents the modulation index. So it represents the modulation index in am. So value of mu is 0 less than or equal to mu less than or equal to m. So this becomes mu square by 2 plus mu square by 2 plus mu square. Since the maximum value of mu is 1, so maximum value of figure of merit, so figure of merit maximum value is 1 by 2 plus 1, which is equal to 1 by 3. So the maximum figure of merit in the case of am is given by 1 by 3. In the case of FM, so when FM signal is transmitted and in the channel white noise is being added, so when it is passed through band pass filter, you will get S of t of FM plus narrow band noise. So this is passed through a frequency discriminator. So the demodulator is called as frequency discriminator. So there are different types of demodulators in FM. So generally it is called as frequency discriminator, and at the output you have m of t plus the noise signal. So here we'll calculate S0, N0. So the ratio of S0 by N0 is calculated, which is called a signal to noise ratio at the output of receiver. Similarly, Si divided by Ni, that is signal to noise ratio at the input of receiver, is calculated. So if you do the analysis by taking this modulated FM signal and white narrow band noise, so we'll get it as the figure of merit in the case of FM is 3 kf square into P divided by FM square, where this kf is called as frequency sensitivity of modulator. Frequency sensitivity of modulator measured in hertz per volt. So it is defined as it is given by in hertz per volt, and is given by the how for 1 volt change in the amplitude of message, how much change in the frequency of the carrier occurs is given by the term frequency sensitivity. And P is power in the message signal m of t. P is power in the message signal m of t. FM is the maximum frequency of m of t, maximum frequency present in m of t. For single tone modulation, so this is the generalized formula. So this is the formula for a general case. For any case we can apply this formula, and for single tone case, so m of t is equal to am cos 2 pi fm into t. So am of t is equal to am cos 2 pi fm into t. So therefore P is equal to am square by 2. So this is the maximum value, so power is RMS value, so AM by RMS value is maximum value by root 2, so AM by root 2 whole square, so you'll get it as AM square by 2. So when you substitute this value of P here, then figure of merit now becomes 3 kF square into AM square by 2 FM. So 3, this by in between as 3 by 2 into kF into AM by FM whole square. So this kF into AM by FM is called as beta. So beta is equal to kF into AM by FM is called modulation index in FM. So this is totally beta now, so its value is equal to 3 by 2 beta square. So these two results are very important and should be remembered. In the case of phase modulation also, so when the phase modulated signal is passed through the channel, so it gets added with white noise, and when it is passed through band pass filter, same you'll get narrow band noise. And since there is relationship between FM and PM, so we'll use the same frequency discriminator. So frequency discriminator is used, so we'll get the message signal plus the noise signal, and we'll calculate S0 by N0 here and Si by Ni here. So this ratio is called as figure of merit. The ratio of signal to noise ratio at the output of receiver to the signal to noise ratio at the input of receiver is called as figure of merit. So in the case of PM, its value is given by Kp square into P, Kp square into P, where Kp is called as phase sensitivity of modulator, phase sensitivity of modulator, and P is called as power in the message signal M of t. So this is the generalized formula for figure of merit in the case of phase modulated signal. So for single tone case, for single tone modulation, so M of t is equal to AM cos 2 pi FM into t. So as we have discussed earlier, so P is equal to AM square by 2. Therefore the figure of merit for single tone case is Kp square into AM square by 2. So now this becomes Kp into AM whole square divided by 2. In the case of phase modulation, we know that Kp into AM is equal to del phi, which is called as phase deviation, and it is also equal to beta, which is called as modulation index in PM. Okay, that is phase modulation. So Kp into AM can be replaced by beta, so it is equal to now beta square by 2. So the figure of merit for single tone PM is beta square by 2. So these two results must be remembered, which are very important. So the last question is regarding the comparison. So regarding the comparison of different analog communication modulation schemes in the presence of noise. So in the presence of noise, which is the best modulation scheme? So in the presence of noise, which is the best modulation scheme? So this problem or this question can be solved by using the value of figure of merit. So if the figure of merit of any modulation scheme is higher, higher is the figure of merit, then better is the performance under noise condition. Better is the performance under noise conditions. Okay, so we have to see for which modulation scheme the figure of merit is higher. So for DSBSC and SSB, so for both these modulation schemes the figure of merit is equal to unity. So second, in the case of AM, we have seen the maximum value of figure of merit is, so the maximum value of figure of merit is only 1/3. So in FM we have seen the figure of merit for singleton case is 3/2 beta square. So we know that beta is always greater than, very much greater than 1. So taking beta almost 5, so this is general case, so beta is equal to 5, so it will be around 3/2 into 25, so which is equal to 75/2, which is equal to around 37.5. So next is for phase modulation PM. So in this case the figure of merit we have seen beta square by 2. So for same value of beta, so it will be 25/2, which is equal to 12.5. So if you compare all the modulation schemes, the figure of merit for FM is very much high when compared to all other modulation techniques. So the better performance is given by FM. So FM will have the better performance under noise. Similarly, AM will have the worst performance under the presence of noise, because its figure of merit is only 1/3, which is least in all the modulation schemes. So it is the worst modulation technique.